Okay, we're going to look at the Lewis structures of phosphate, phosphite, and hypophosphite. A couple of three polyatomic ions. Whenever I draw a Lewis structure, I like to keep an accounting of how many electrons are in the molecule, and I encourage you to do the same thing. Draw yourself a T-chart, put atom on one column and the number of valence electrons on the other. That's what number of VE stands for. Some people call that hashtag now, but it used to stand for a number. Phosphorus, oxygen, and then the number of electrons. So if the polyatomic ion has a charge, you add 3 electrons to your accounting. Phosphorus is a group 15 element, so it has 5 valence electrons. Oxygen is a group 16 element, so it has 6 valence electrons, and there are 4 of them in phosphate. So the total number of electrons is 32 for phosphate. We're going to start by writing the central atom as phosphorus. We're going to bond each oxygen atom. And then that's going to use up 8 electrons, because 2, 4, 6, 8, each one of these lines stands for 2 electrons. That means we still have to account for 24 more electrons. And what I did is I placed 6 electrons on each oxygen atom, times 4. That uses up 32 electrons. Then what I did is I made sure that every atom in the polyatomic ion has a completed octet. So you see that oxygen has 2, 4, 6, 8. Remember that when you're counting octets, bonds count for 2. So although they're shared, you still count them for 2 for whatever atom you're counting an octet for. So you can see that all the atoms, all the oxygen atoms have fulfilled octets. Phosphorus has 2, 4, 6, 8 as well. So phosphorus has a fulfilled octet. Then we account for charges. When you account for charges, you count how many valence electrons the atom normally has when it's neutral. And remember to count shared bonds as 1. So this oxygen atom has 2, 4, 6, plus another 1, 7. Oxygen atoms like to have 6 valence electrons, so because it has 7, and it would normally have 6 when it's neutral, you'll have to put a negative charge on there to show that it's accommodating more electrons than it normally wants. The same applies for all 3 other oxygen atoms in the molecule. Phosphorus is group 15, likes to have 5 valence electrons. When you count the bonds, each one counts for possession of 1 electron for charge consideration. So 1, 2, 3, 4. And that's why you put a plus charge on the phosphorus atom. This is a preliminary structure. When you see that the structure has a lot of formal charges, you try to re-engineer the shape so that you can reduce the number of formal charges. And what I did here was I took a lone pair and I turned it into a bonding pair. And that's why now the modified drawing shows a double bond between phosphorus and oxygen. All the other ones remain the same. This is not actually what the molecule looks like. It's a snapshot of the accounting of electrons. In reality, what you have is 5 bonds shared over 4 positions equally. So really, you could say that phosphate has 1 1/4 bond character. If that double bond, recall that electrons are moving at 2/3 the speed of light, and they're whizzing around in there, equally distributed between the phosphorus atom and the oxygen atom. So each of these positions has a double bond for the briefest time period, but it's time averaged. So that in the end you get 5/4 bond character. Let's draw another one. We'll start with the T-chart. Phosphorus, oxygen, number of electrons. Phosphorus always has 5, oxygen is 6, and there's 3 of them in this one. And the charge is also 3. So 18 plus 8, 26 electrons have to be accounted for. We start by drawing, let's make some room first of all. We'll start by drawing the central atom, phosphorus, and then the 3 oxygen atoms. That uses up 6 electrons. Now we still have to use 20 more. So we'll put 6 on each one of the oxygen atoms. That uses up the 18. The last 2 I'm going to put on the central atom. When we look at the octet, every one of these atoms has a fulfilled octet. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, and for the phosphorus atom, 2, 4, 6, 8. All of them have fulfilled octets, so that's a good sign. If we check for charges, oxygen likes possession of 6 electrons, but actually possesses 7 in this configuration, so we're going to put a minus charge. All the other oxygen atoms have the same thing. Phosphorus likes possession of 5 electrons, because it's a group 15 element, and it has 1, 2, 3 plus another 2, so it's neutral. and you don't put a charge on the phosphorus, the overall charge on the molecule is -3. So you don't have to modify it in any way. This would be with phosphate, that would be the correct Lewis structure for phosphite. For hypophosphite, by the T-chart, phosphorus, oxygen, electrons, 5, 6 for oxygen, there's 2, and the number of electrons is 3, because again, the charge for all 3 of these polyatomic ions is -3. So the total number of electrons in hypophosphite is 12 plus 8, or 20 electrons that have to be accounted for in the Lewis structure. We'll start by drawing the central phosphorus atom, putting the oxygens as satellites. That uses up 2, 4 electrons. So now we have to account for 16 more electrons. 2, 4, 6, 8, 10, 12, 14, 16. Okay? Checking for your octets. 2, 4, 6, 8. Oxygen has a fulfilled octet. Phosphorus, 2, 4, 6, 8. Fulfilled octet. This other oxygen, 2, 4, 6, 8. All of them have fulfilled octet. Good sign, we can continue from there. Now let's check for charge. The way we've drawn the oxygen atom, it's going to have a negative charge. Why? Because it wants 6, but it has possession of 2, 4, 6, plus the 1. When you count for charge, it's only 1 for a bond. So you have 7 electrons in proximity of oxygen. So oxygen is going to have a formal charge of -1. Same with the other one. Phosphorus likes to have possession of 5, but in this configuration it has 2, 4, 5, 6. So in this case, even the phosphorus atom would have a negative charge. So the molecule, again, still has an overall charge of -3, but the phosphorus is also carrying a negative charge, which would probably explain why hypophosphite is likely not a very stable polyatomic ion. The presence of the highly electronegative oxygen atoms probably withdraws the extra electrons towards them, but that's getting into more complicated stuff. We can leave this as the final Lewis structure for phosphate. It has the correct number of charges, and each one of the octets is fulfilled. Edit that. Any questions? Any questions? No?
Wait. See, for the last one, the hypophosphite,
Yep.
you counted 8, so why is there 7 now? For the oxygen.
I counted 8.
Yeah, you said that it's 8.
Okay, fair enough. I counted 8 for, there's 2 things that I'm going to count. The octet requirement and the charge requirement. For octets, it's sufficient for an atom to be sharing an electron for it to be counted as its own. So when I'm doing octets, the bonds, which represent shared electron pairs, still count as though they belong to the atom. If you were to draw how octets are counted, you would go like this. Okay, so this oxygen atom thinks it owns all these electrons. This phosphorus atom thinks it owns all these electrons. And this oxygen atom thinks it owns all those electrons. But for charge, you would count it this way. I'll redraw the molecule. For charge, you would count it this way. Okay, so counting on octets looks like this. Counting charges looks like this. Looks a little like a dog's nose, doesn't it? Okay.
So 2, 4, 6, 7, 2, 4, 5, 2, 4, 6, 7.
Okay, for this, look, for this one, for the octets, 2, 4, 6, 8. For this one, 2, 4, 6, 8. And for this one, 2, 4, 6, 8. So the octets here are all done. They're all good. Now for charges, because they're sharing, they only count for 1. That's why they don't overlap. You know, these 2 electrons are shared. So the oxygen atom actually only possesses 1 of those, and it possesses the lone pairs. So for charges, you'd say 2, 4, 6, and then plus 1, 7. 2, 4, 6, plus 1, 7. And for phosphorus, it'll be 2, 4, 5, 6. Okay? And then, of course, you have to compare it to what it would want to have from where it appears on the periodic table. You'll stop it there.